welcome to the inaugural Millie Dresselhaus Memorial Lecture. And I should say that all her students and colleagues call her Millie fondly. She was a leader in research on the electronic behavior of materials, particularly carbons. And she was an experimental solid-state physicist, a student of Enrico Fermi, a Nobel laureate. She has received numerous awards, including these: National Medal of Science, Buckley Prize from the American Physical Society, the Fermi Award, the Kavli Prize, the Materials Research Society von Hippel Award, the IEEE Medal of Honor, and the Presidential Medal of Freedom, Honorary Doctorate from Oxford, UNESCO Medal, Franklin Medal, etc., in chronological order. However, she said in 2016, one does not work for the purpose of getting awards. It's the love of science. I graduated from Caltech in 1973 as one of the 4 first women graduates of Caltech. And after that, I moved on to MIT, and I took Millie's solid-state physics course, and I fell in love with the beauty of the physics. And so I started working with Millie as her PhD student. Millie was a violinist, and I a pianist. And so Millie invited me to her home for dinner and an evening of chamber music. And afterwards, she drove me back to Tang Hall, my dormitory. And she was very gracious in entertaining students at her home. She and Jean, her husband, had 4 children. My first assignment from Millie was magnetofreflection, a very difficult task because it involved high magnetic field, cryogenic temperature, electronics, and optics. And Millie saw that I was having difficulty, and she told me, "We'll be patient with you." And this is my very first paper, magnetoreflection of graphite. And Millie figured out my name, publication name. You know, I have always been using my name Deborah Chung, but I have Chinese name in the middle, actually, Dun Ling. So Millie figured out D.D.L. Chung would be the name. And Millie gave me the topic of converting graphite to a metal by intercalation. And we were both new to this field, and she started me by going to chemical abstracts and Xeroxing the abstracts that are relevant and pasting the abstracts on a piece of paper and just handing me the paper. And that was how I started the research. In 2014, 37 years after my graduation from MIT, Millie sent me this email. She said, "Deborah, your thesis work is historical for me as an early work on a single graphene layer where intercalants were used to separate the layers. My nanoscience efforts went from graphite intercalation compounds to fullerenes after their discovery, and this led to the idea of stretching out fullerenes from C60 to C70 to C100, and perhaps making a tube that would be a single layer of carbon atoms in thickness." And here is a slide from a 2011 lecture given by Millie on graphene and nanotubes. And this slide shows the growth of the carbon science field based on the number of publications per year. The nanotubes here and then graphene here. Big advances. After graduation from MIT, I continued researching on graphite intercalation compounds. However, 16 years after graduation from MIT in 1993, I invented smart concrete, which is concrete having a little bit of short carbon fiber so that it is a sensor. This means self-sensing structural materials, the structure sensing itself. No device involved. Thus, low cost, high durability, no mechanical property loss, and also design simplification and large functional volume. And the attributes sensed include stress or strain, damage, and temperature. And smart concrete propelled the field of multifunctional or smart structures. In 2016, Millie said, I was in my 70s when I started research on graphene. And then when she was 80 years old, which is 6 years before her passing, she gave this beautiful lecture in UK on Raman spectra of graphene and carbon nanotubes. This is on YouTube. With what Millie said in mind, I'd like to talk about today something really new: the dielectric and electret behavior of electronic conductors and the associated new avenue of electrical energy generation. This is a new field that I started in 2019 with more than 30 journal publications at this point. Electronic conductors are materials that are most conductive, including metals such as steel and carbons such as graphite. The dielectric behavior means electric polarization behavior, that is, giving an electric dipole, and thus a capacitance, and the corresponding material property is the permittivity. The dielectric behavior is a new chapter in the electrical behavior of electronic conductors. It's because this has escaped attention due to the high conductivity and the consequent low electric field. Jonscher predicted theoretically in 1999 giant polarizability in conductors. Unfortunately, he passed away 6 years after this prediction. I made the first experimental observation of relative permittivity as high as 10 to the 6th in conductors in 2019, which was 20 years after the prediction. Now, electromagnetic shielding, or EMI shielding, exploits the permittivity for the absorption of microwave radiation. But this work that I'm going to talk about involves not microwave, but low frequencies such as 60 hertz or even DC. Now, in order for an electronic conductor to be polarized, a fraction of the mobile charges, such as the electrons, has to interact with the atoms. If there's no interaction, then the electrons just loop around without any polarization. But here there is some interaction, so there is some polarization that's possible. Now, the electric field that can be sustained in a conductor is small. However, the electric field needed to cause carriers in a conductor to move is also small. Now, the polarization impedes DC conduction, so it increases the apparent resistivity. In other words, the polarization gives rise to a voltage that has a polarity that opposes the voltage that's applied for the sake of conduction. As a result, the material looks like that the resistivity has gone up. So as the polarization takes place, the resistivity builds up. But when one reverses the polarization, reverses the polarity rather, then the polarization doesn't change instantaneously, so you end up having the polarization aiding rather than impeding conduction. So the apparent resistivity drops from R1 to R2. And afterward, if you keep on having that reverse polarity, then you have depolarization or even reverse polarization. The average of R1 and R2 equals the true resistance in case of electrical symmetry. The apparent resistivity increase is disadvantageous for conduction applications, whether it's for electrical interconnections, electrical contacts, electronic device components, electrochemical electrodes, or heating elements. Solder is important for electrical interconnections, and that's metal, and that's electronic conductor. So this is the real data showing the apparent resistivity increase during polarization, the drop during the polarity reversal, and then this depolarization followed by reverse polarization. Obviously, the higher the current, the more is the effect. Note that the reverse polarization is less than the forward polarization. There's asymmetry involved. In other words, the forward polarization is more. The forward and reverse polarization are obvious opposite in direction, but the magnitude is more for the forward than the reverse. And interestingly, there's no polarization saturation. It keeps going. The polarization keeps increasing as the applied electric field increases. So this is ferroelectric or paraelectric behavior, whatever you like to call it, in a metal. Now, I mentioned about the asymmetry, and this is a similar asymmetry as noted for nickel and aluminum, two other metals. However, if one short circuits the two electrodes immediately before the testing and short circuit it for 6 minutes, one forces it to be symmetric. Okay? That is, the electrical asymmetry is naturally there. To kill that asymmetry, you have to depolarize it right before the testing. Similarly, it happens for carbon fibers. Shown here are uncoated and nickel-coated carbon fibers. Again, naturally, it's asymmetrical, but if you depolarize it right before testing, then it becomes kind of symmetrical. Now, carbon fibers are very important for lightweight structures because of their low density, high modulus, and high strength. And they are widely used for aircraft, also for cars, and for turbine blades, and for retrofitting concrete structures, and for robot arms, and so on and so forth. Now, the most basic material property concerning the dielectric behavior is the permittivity. And for probing that, one needs to measure the capacitance. Now, measuring the capacitance of a conductor has pitfalls because an LCR meter is not designed for measuring the capacitance of a conductor. So we put a thin insulator, double-sided adhesive tape in red here, in between the specimen and the electrode so that the overall material system has a high enough resistance for the LCR meter to behave properly. Okay? Now, but then we need to decouple between the volumetric and interfacial contributions to the measured capacitance. And the interfacial contribution includes that dielectric film. And to decouple, we measure the capacitance for 3 or more different thicknesses of the specimen and plot 1 over capacitance versus the inter-electrode distance or the thickness L. And we get a straight line, and the slope relates to the relative permittivity, which I call kappa. Okay? And so in this way, we decouple the volumetric and interfacial capacitances. And this is real data for tin for silver solder alloy, and shows real linearity. And from the slope, the permittivity, the relative permittivity, is about 10 to the 6. That's really colossal permittivity. And this linearity points to dipoles in series, that is, capacitors in series. Now, polycrystalline graphite is widely used for electrodes for the electrochemical reduction of metal ores to form metals. They are really big. And they are also used for heating elements. And they are available commercially at different grain sizes. So we investigated the effect of the grain size on the permittivity. And we find that the grain size increases a lot with decreasing, the permittivity increases a lot with decreasing grain size. And we can plot the relative permittivity versus 1 over grain size, which relates to the grain boundary area per unit volume. Then we get a straight line, meaning that the permittivity involves electron-atom interaction, which occurs at the grain boundaries of the polycrystalline graphite. Now, not only does grain size refinement enhances the permittivity, cold working also does. We can't cold work carbons, which are too brittle, but we can cold work metals. Now, cold work means plastic deformation at temperatures below the annealing temperature. And indeed, for both copper and steel, we see that the relative permittivity increases substantially after the code work in the form of rolling or drawing. So the microstructural effect of plastic deformation, which involves dislocation generation as well as grain size refinement, increases the amount of sites for the electron-atom interaction, thereby increasing the permittivity. Bending affects the capacitance also, but in the opposite direction. This is the capacitance versus the radius of curvature of the bending, and the capacitance decreases as the radius of curvature decreases, meaning the bending decreases the capacitance. Okay. And one can instead look at the effect of the number of bends at the same radius of curvature on the capacitance. And again, we find that the capacitance decreases with increasing number of bends. Why is that so? Why does the bending decrease the capacitance? That is because the bending hinders the dipole-dipole interaction. Whether you consider dipoles in series or dipoles in parallel, when you have a bend, you would have less dipole-dipole interaction across that bend, and that means less dielectric continuity. That's an idea that I came up with. Dielectric continuity helps the polarization, and it's more demanding than conduction continuity. Now I'd like to move on to another aspect of dielectric behavior, and that is the electret, meaning a permanent electric dipole. Non-conductive forms of electrets in the form of ceramics and polymers have been around for decades. But what's new here are electrets that are conductive. Now, for non-conductive electrets, the polarized state is thermodynamically stable. And the depolarized state is thermodynamically stable. Okay? So because the depolarized state is thermodynamically stable, it undergoes self-discharge. On the other hand, for the conductive electret, the polarized state is thermodynamically stable. And the depolarized state is thermodynamically unstable, just opposite. As a result, for the conductive electret, it undergoes self-charge, not self-discharge. Well, we all know that battery charging requires electricity input. It's not self-charge. And we all know that a battery undergoes self-discharge, and that's why the shelf life of a battery is limited. Okay? I should also mention that the non-conductive electrets requires poling, as you can expect, because the charge state is not thermodynamically stable. But a conductive electret does not require poling, as expected from the fact that the charge state is thermodynamically stable. Poling is not so great because depoling occurs afterward. But for the conductive electrets, we don't have to worry about depoling. Poling is not feasible for a large structure anyway. So let's measure the electret voltage versus the inter-electrode distance for this alloy. This is before polarity reversal, and this is after, and obviously there's a sign change after polarity reversal, obviously. And note that the magnitude of the voltage increases with increasing inter-electrode distance, really Ohm's law, and that means long length is advantageous. The electric field in the electret is the voltage divided by the inter-electrode distance, and that increases a little bit with increasing inter-electrode distance L, and also changes sign upon polarity reversal. And this slight increase in electric field with increasing L points to dipoles in series. And that is in agreement with what I said earlier from the plot of 1 over capacitance versus L, and that linearity points to dipoles in series. Now what's very interesting is that the electret can discharge upon short circuiting. And during the discharge, the electric field or the voltage decreases gradually to 0. And afterward, if one open circuits it, just let it sit, it charges back up automatically. That's self-charge. Okay, this is data for graphite. And we also looked at the effect of the grain size of the graphite on the voltage or electric field. And the smaller the grain size, the bigger is the effect. And the resistivity also has the same trend. But the relative permittivity, this has same trend, but it's more dramatic trend. The permittivity increases more dramatically with the grain size reduction. So the electric field is governed more by the resistivity than the permittivity. This is similar data, but for a metal as opposed to graphite. It's similar behavior, except that the discharge time is now shorter, like 40 seconds as opposed to 400 seconds, because the alloy is more conductive than the graphite. Now, by getting the current, which corresponds to the voltage, and integrating the curve of current versus time during discharge, one can get from that shaded area the electret charge, which I call Q prime. And from that Q prime, one can get at the fraction of carriers that participate in the electret, and compare then with the separately determined fraction of carriers that participate in the permittivity. And one finds that the fraction of carriers that participate in the electret is much higher than the fraction of carriers that participate in the permittivity. Okay, -4 versus -12, for instance. Also, the fractions are small, whichever fraction, and either fraction increases with decreasing grain size. And the fractions are smaller for metals and carbons because metals has a lot of free electrons. Now, the code work that I mentioned before, not only does it increase the permittivity, it increases the electret voltage too. This is the electret's electric field versus the amount of prior code work for copper. The code work, again, involving code rolling. Again, it's electron-atom interaction that's enhanced by having more sites for that interaction. But very interestingly, the positive end of the electret voltage is located where the rolling induced plastic flow originates. That means the electrons move along with the atoms during the plastic flow, a clear indication of electron-atom interaction. Now, the electret discharge is really capacitor discharge, but the capacitance is not the usual permittivity-based capacitance, but it's a new capacitance that I termed electret-based capacitance, which is defined as the Q prime, which is the charge in the electret, divided by V prime, which is the voltage of the electret. Q prime drives V prime. In contrast, for the permittivity-based capacitance, it's good old Q over V, with V driving the Q. The C prime is higher than C by as many as 16 orders of magnitude. Say C prime can be 10 to the 5 farad, and C 10 to the minus 11 farad, for instance. Okay. Now, discharge time constant, we know is RC for an ordinary capacitor, but now it is RC prime, with the C prime being the electret-based capacitance. And this discharge energy for a capacitor is good old half CV square, but now is half C prime V prime square. And experimentally, we show this to be true for a variety of metals and carbons. Aha! This is a word Millie loved. She said, at some level, aha moments comes once a week. She was referring to her weekly group meetings. When we are working on a problem at the cutting edge, you always have a surprise. And I was really surprised because I was guessing, wow, I need to get a theoretical physicist to work out all the quantum mechanics to figure this science out. But it turns out to be very simple. Now, I mentioned that we have experimental support of that very simple model. And here it is. For a variety of metals and carbons, we calculate the discharge time constant, RC prime, and measure the discharge time constant. The discharge tends to be faster for metals than carbons. And for all the red rows, the agreement between the calculated and measured values are kind of okay. Not all of them are okay, though, but most of them are kind of okay. And the discharge energy, we also compare the calculated and measured values. And the agreement is kind of okay for the majority of these materials. For the carbon fibers in these two last rows, the agreement is not good. I believe that is the anisotropy of the carbon fiber toe that causes this model to not work as well. All the other materials that have the model work kind of well are isotropic. So the model is very simple. It's just capacitor discharge and charge, but the capacitance is the electret-based capacitance, not the usual permittivity-based capacitance. Now, the discharge time increases with the interelectrode distance L, and this is experimental data, which actually agrees with the model. The thermodynamics of the discharge and charge. For both electret-based capacitor and the good old permittivity-based capacitor, the discharge is due to entropy increase, same thermodynamic driving force. But the discharge is different for these two. For the electret-based capacitor, the charge is due to enthalpy decrease, whereas for the permittivity-based capacitor, the charge is due to entropy decrease. Now, there's been quite a lot of interest in the last 10, 20 years on getting energy from a structure. In fact, I was a pioneer in this field back in 2001. Structural battery or structural capacitor, meaning having a structural composite be able to provide battery or capacitor function. And this involves device incorporation. However, the device incorporation weakens the structure, and the device life is much shorter than the required service life of the structure. So this route of getting energy out of a structure is not so great. However, what I'm talking about today involves no device incorporation. Now, speaking of structural materials, steel is very important. Okay? And steel is an electronic conductor. So we did the same experiment for steel, and it works out similarly. And the electret voltage increases with increasing interelectrode distance L. However, the next question is, how about the effect of the cross-sectional area on the electret voltage? Okay. So we took 10 different widths of steel bars, each 6 feet long. So we have 10 different cross-sectional areas, A, and we studied the electret voltage V prime versus A and found that the voltage increases with A like so. In the low A arena, the V prime is roughly linear with the A. But in the high A arena, it's not linear, but still the V prime keeps increasing with increasing A. Okay? And this is because the A increases the Q prime, and the Q prime drives the V. And this also points to the capacitors being not in parallel, but in series. Okay? If it's in parallel, having more capacitors in parallel is not going to increase the voltage across the capacitor. However, with capacitors in series, you have the A increasing the Q prime and the Q prime driving the V prime. And so the capacitance of each capacitor in series is proportional to the area A. However, this requires transverse electrical connectivity, which is exhibited by steel, which is isotropic. And this dipoles in series or capacitance in series, I already mentioned before, as supported by the fact that the 1 over capacitance increasing linearly with the interelectrode distance L. Now, the nonlinear behavior in the high area regime, I believe, is due to the decrease in resistance with increasing A, and the fact that the dielectric and conduction behaviors are actually related. Now, the electric power is good old V squared over R, but now is V prime squared over R. And as A, the area increases, the V prime, the numerator, increases, and R, the denominator, decreases. So the power would increase a lot. And that's what happens. And so the power increases by like 50,000% with the increase in area A. Now, for carbon fiber tow or bundle, there's inadequate transverse electrical connectivity. And that transverse connectivity is required for the significant increase in voltage with increasing area. So we don't see that much increase in voltage with area for the case of carbon fiber tows. Now, the electret is strengthened by mild heating to, say, 70 degrees centigrade. The electret voltage or electric field increases reversibly. The relative permittivity also increases reversibly, but the fractional change in permittivity is much smaller than the fractional change in the electric field. And this effect can be used for temperature sensing as well as thermal energy harvesting. The electret is also strengthened by elastic tension, thus allowing stress-strain sensing and mechanical energy harvesting. The electric field increases reversibly upon tensile stress, and same for the permittivity, but the fractional change of the permittivity is smaller than the fractional change in the electric field. That means the carrier-atom interaction is promoted by the tension. We are all very concerned with energy, and wind energy and solar energy are expected to be increasingly important in the future. But both solar and wind energy is generated intermittently, so energy storage is required, and the energy storage involves mainly batteries, and that involves cost, volume, and weight. Now, the electret-based energy generation can provide continuous discharge-charge cycling, and with different parts of a structure starting discharge at different times, energy can be continuously provided. That means on-demand energy generation, and no energy storage is needed. And the electret-based energy generation is more effective if you have large structures. And we have a lot of existing large structures in any city. And this is a new untapped form of energy, clean with no greenhouse gas emission. And I do have an issued patent on this. And I call this structural energy. It's also structural self-powering. Okay? And it's using big structures to provide energy. Actually, there are two energy applications. One is energy generation, what I've been talking about, and fast discharge is preferred for that because then you can have a lot of discharge cycles per unit time. However, another application is as a power source, which would prefer slow discharge. Okay? So let me talk about the second energy application, the application as a low voltage power source. And we discovered that to be feasible for flexible graphite, which is a form of graphite made by the compression of exfoliated graphite. And there are a lot of cells in the exfoliated graphite. And so the flexible graphite has a cellular structure and a lot of interfaces in the flexible graphite, whether within the cell wall or between the cell walls. And interfaces are great for sites for the electron-atom interaction. And so the flexible graphite turns out to be very strong in the electric behavior in the sense that it doesn't discharge easily. And we have a discharge time greater than 700 hours. Okay? And we can further increase this discharge time by adding a load resistor. Again, RC time constant. Having more R would increase the discharge time. And this is our piece of flexible graphite. And it is two-dimensionally isotropic, so there's transverse as well as longitudinal electrical connectivity. And we have 4 electrodes, the 2 outer ones for current and the 2 inner ones for voltage. And we measure the voltage between the voltage contacts using a nanovoltmeter. And we hook up to the current electrodes a load resistor. And indeed, current goes through this load resistor, and the current level is just as expected, being the electric voltage divided by the sum of the load resistance and the resistance of this piece. To be exact, the 2-probe resistance of this piece of flexible graphite. So the electric voltage in flexible graphite drives current through a load resistor in the circuit. And we've confirmed that with different values of the load resistance. Now, thermoelectric energy generation is very well known. It has been researched for decades. And thermoelectric materials are also electronic conductors, but they require temperature gradient in order to provide a voltage. Also, there's limited choice of materials because it requires high thermal power, low thermal conductivity, and low electrical resistivity. It has to have all 3 things going for you, and that's why it's so challenging. And also, they are not structural materials. Now, a lot of future research awaits, particularly to tailor conductors for the dielectric behavior, relating the processing to the structure and the structure to the properties. The property particularly being the dielectric property. Okay? And in this work, I'm introducing some new scientific concepts, namely carrier-atom interaction in conductive materials, polarization in conductive materials, electrets in conductive materials, and dielectric connectivity or continuity. And this is really a field in its infancy. This work also connects fields that are disconnected, that is, conduction behavior versus dielectric behavior, conductive materials versus non-conductive materials, and structural materials versus electronic materials. And this work does not conform to the current trends in materials research. These current trends emphasize material modifications, nanomaterials, materials designed by computation, and the trends also move from materials to material systems and moves away from core material science. I appreciate the partial support of this work by the U.S. Air Force, which is interested in electric aircraft. My many thanks to Professor Dresselhaus for introducing me to scientific research. She said, the most important thing that a professor teaches is not fact, but how to do science. She also said, a broad education is the key. Millie is known as the queen of carbon science, and there's a new book called Carbon Queen by Maya Weinstock, just came out, and this is a biography of Millie. And back in 2018, I had this book, Carbon Materials, published, and I dedicated this book to the memory of Professor Dresselhaus. This is her citation record over the many years, and it just keeps rising until she passed away, and then it just started to decline a little bit. And her citation record is just tremendous, and this is really inspiration to all of us. With humility, I'd like to dedicate this lecture to the memory of Professor M.S. Dresselhaus. I'd like to mention about Professor Klaus Biemann of MIT. He is known as the father of organic mass spectrometry. And the inaugural Klaus Beeman Memorial Lecture will be given in 2023. In fact, I helped him in his biography, and I actually coined the term father of organic mass spectrometry for him. The second Millie Dresselhaus Memorial Lecture will be given in 2024. Thank you.